Hey, so I'm currently making my video that I will turn in about 9 hours. Um, well, started. My topic is quantum levitation or quantum locking, and it's part of the um, quantum physics section in the textbook. So you might be wondering, when did I become an expert in quantum physics? Last night. So, what is quantum locking? Basically, it's a process where you have a superconductor and it's frozen in liquid nitrogen and it's placed within a magnetic field, but the superconductor is locked in the magnetic field. This is a result of the Meissner effect. Now, what is the Meissner effect? Well, it was discovered in 1993 by German physicists Walther Meissner and Robert Oschenfield. They were measuring magnetic fields surrounding certain materials, and they found out that if you superconducted or cooled cooled the material to the point where it became superconducting, the magnetic field intensity would drop to zero. What does this mean? Well, it means that electrons are able to flow with virtually no resistance. Now this makes it easy for the material to lock in place, and it cancels out the effect of the magnetic field, which holds it in place. And yeah. Alright, this is an example of flux pitting. This is the reason quantum locking can happen. So basically, the superconductor cannot be penetrated by the magnetic field, and this is what makes this flux pitting possible. On the bottom, you see the magnet, which creates the magnetic field. The top, where the circle is, you see the superconductor. It's a small disk that's usually frozen in liquid nitrogen, and this helps create the superconducting effect to cool down the material. Around, you can see the magnetic lines being stretched, and since it goes around the disk and through the disk, it kind of looks like a harness. This is what holds it in place and helps it levitate. I've been talking about superconductivity, and if you don't know what it is, basically it's the quantum phenomenon where the material can reach zero electrical resistance. This can only happen if the object or material, whatever it is below a certain critical temperature. It's a really low temperature, and this is what helps create the Meissner effect. So basically, when the object is superconducted lower than its critical temperature, or its TC, as you can see in the last picture, the magnetic lines will form. Here's the object. The magnetic lines will go around the object, and this locks it in place. And this is what Meissner found, which coined the term the Meissner effect. That's really all I have to explain. It's a simple concept, but very interesting. At least I found it very interesting. There's a YouTube video that will play that will show you the exactly what I explained, the Meissner effect, the quantum locking, all because of the superconducting material, and show you different examples and what they use it for.
So what if we got here?
So we have quantum locking. The superconductor is locked in space, and it stays wherever I put it. You see, this is quantum trapping.
It's amazing.
As long as it's
so the
cold,
it's superconducting. It's frozen with liquid nitrogen.
Upside down.
Right.
And it stays locked.
So the fact that it's superconducting is locking the magnetic field in three dimensions, right?
Yeah, exactly.
And that
and
pivots.
You see, because this is symmetric, it can rotate without break the locking. The locking doesn't break.
Right.
Because
it stays there on the X and Y, but not on, it pivots on the
on the axis of the magnets. You see, if I can move it on the side, it will again pivot around the axis of the magnet, because it makes sure that the magnetic field inside of it stays the same.
Right. It's astonishing. Can you put it on the track for us?
Yeah. I just levitated above the track quite high, and I can just rotate it.
So it's actually floating above the surface.
Yeah, it's not floating, it's locked above the surface.
So you could tilt it at an angle and it would
Yeah,
still fly
I can
around.
do it like this, and it will just go around like this. I can just go and put it at different height, and then like this.
And lock it at the height.
Lock
right?
it, yeah, different height, different configuration.
Right.
And I can even lock it at opposite way. If you could just hold for a minute. Hi. I'm doing the same
it can
thing.
hang
I'm
upside
locking
down.
it upside down, and then it is suspended.
Fantastic. Okay.
That was a great video. So you're probably wondering, what can you use this for? You know, what real-world applications is there to quantum locking? Well, imagine lifting a very heavy object. And, you know, nothing else can lift. You probably have to set up a crane for it. With this, with this technology, you can lift that material and bring it to different heights, whatever you want, and keep it there, whatever height you want, because, like you saw in the video, the y-axis will lock. So if if they hone this technology, they can make that happen. Imagine trains, since it's almost frictionless. You saw in the video the superconducting material going around the track. And it was, like I said, frictionless. Won't take much energy. It'll take a lot of time to make though, but you just need some magnets and superconductive train. And to stop the train, you just heat up the train, and since it's heating up, the magnetic lines will stop holding the train in place, start doing something, and it create more friction, physics, and it would somehow stop. It'd also be used for something simpler. Like imagine a large round bar, and everyone's sitting around. It's like almost a table-like thing, but bartender and all the material bartender uses in the middle, and the bar is around it. It's huge. The bartender can just take whatever, he's at his station, take whatever cup, put it on that material, push it around the bar, and whoever it is, they can stop it, grab the cup, and yeah, it's pretty freaking awesome, if you ask me. I mean, come on, it's freaking levitation. Like, how's that not cool? Just magic trick. It's another application. Stand on top of the material. And you're levitating. Have some superconductive shoes. Step on top of a magnetic field, and you're good. And tilt your shoes at a 45-degree angle. You can be standing like this. That'd be cool too. I'm running out of stuff to say, so yeah. Honestly, this stuff could probably just cure cancer. Imagine a floating city. Quantum locking, baby. Honestly, I wouldn't even need a freaking bummy ass $30 iPad case anymore. Quantum locking. Tilt whatever angle you want. Oh, sorry. Carry your own magnets. Have whatever magnet you want. Superconduct the back of this ish. You can have it at 90 degrees, 45, whatever angle you want, like you saw in the video. Yeah, 180. Flat up. Upside freaking down if you want. Just laying in bed, have a thingy right here. Like imagine hoverboards, like that movie Back to the Future. Just have your streets lined with magnets. Ride that ish everywhere.
My name is Coach Rice. I teach physics. Physics by day, rugby by night.
can have freaking like floating trash cans. Possibilities are endless. Quantum locking. Am I at 10 minutes yet? No, like actually though, I find this very interesting, very cool. I just wish there's more stuff to talk about because all these examples are hypothetical. And it hasn't been used yet. And all they have is just one little disc on a track or floating in midair. It's still awesome, but yeah, maybe in the future. It's a very simple concept, very easy to understand. Locking, different temperatures, magnetic field lines. We went over that. Yeah, and I hope you learned something.